first challenge in problem solving is to identify the correct given. Here in table 1.1, we have a list of some tips to determine the correct given. For variable acceleration, the hint is it is a given that is distance over time squared. Example units are meter per second squared, miles per hour squared, kilometer per hour squared, or feet per second squared. Anything as long as it's distance over time squared. That's for acceleration, or that is acceleration. For velocity, any given that is distance over time. Example, meter per second, feet per minute, kilometer per hour, centimeter per second. That's velocity. Any given that is distance over time. Next is time. Obviously, any given that is time. We have seconds, minutes, hours, days, months, years. Those are the sample units for time. And x, we have any given that is length. So any given that is meter, kilometer, mile, feet, yard, centimeter, millimeter, light year. These are sample units of length or variable x. Example 1.3. From rest, a motorcycle traveled eastward with a constant acceleration to a final velocity of 0.05 meter per second in 10 seconds. Find the motorcycle's acceleration. So here we are to find the acceleration. And so we need to use any of the equations that we have derived, any of the three, 1.1, 1.2, 1.3. From those, we can choose the first equation, 1.1. But first, we write the given. The given are we have 0.05 meter per second, and it is a final velocity. V sub f is 0.05 meter per second. Since the initial velocity is not given, then it is assumed that it's 0. And time interval is 10 seconds. That's the t final, 10 seconds. And t naught is 0. Find the motorcycle's acceleration. Now the technique is to write first the three equations. If we have an object that is accelerating, we need to use any equation from among the three equations. We have A df minus to equals vf minus vo, and 2a xf minus xo equals vf squared minus vo squared, and the other one is xf minus x naught equals vo df minus t naught plus 1/2 a df minus t. Now squared. Now checking now the given and what we are looking for. We're looking for A, and we have T final, we have T initial, and we have V final, and we have V initial. Obviously, we can use the first equation since we have the unknown A, and this is what we are looking for. And you have all the and all the variables are given. So using 1.1 to solve this equation. Using 1.1 to solve this problem. So let me rewrite that one. And then since t sub 0 is 0, which is always the case, I will drop the t sub 0 now. And we have a t final equals Vf minus Vo. Here we also see that from the given Vo is also 0, so we can also drop now the Vo. So we have ATF equals Vf. And we want A, so we can divide the entire equation by TF. TF. So basically on the left side, we are left with our A because we have canceled TF over TF equals VF over TF on the right side, and we substitute V final is the given, substitute the given 0.05 meter per second over T final, which is 10 seconds. Executing using your calculator, you will get an answer of 0.005, and the unit there is meter per second squared. That's a unit for acceleration, but let's clarify that. So we have arrived at that answer because of this meter per second over second, and this is like division of fraction. We have meter per second times the reciprocal of the denominator. So numerator, denominator, numerator meter per second times the reciprocal of denominator, which is second. Reciprocal of second is 1 over second. Okay, so we have meter per second squared. Thus, this example 1.4. How long can a basketball player stop when running to the plus x direction at an initial velocity of 3 meters per second and decelerating or slowing down at 2 meters per second squared? For the given, we have V initial is equal to 3 meters per second and V final, because the player stopped running, so V final is 0, and A is negative 2 meters per second. Now A is negative since our player is slowing down or decelerating and is traveling to the right or plus x. This means that the player's acceleration vector is directed to the left or negative x because he is slowing down while moving to the right. So the player is moving to the right to the plus x, but it is slowing down. So its acceleration vector is directed to the left, opposite to the direction of motion because it is slowing down. So A is negative A, or acceleration is to the left. And we are to solve here for time. Again, looking at the three equations that we have A, VF, VO, and we're looking for time. We can use the first equation. You can do the checking by yourself. So using the first equation, we have AT equals VF minus VO. I have dropped already the T naught, which is equal to 0. And this is the T final, is what we are looking for. So here we have used T final minus T initial equals our elapsed time T. And this is what we are looking for. So that's why here I only have T. I have already simplified the equation to AT equals VF minus VO only. We want T, so we can divide the entire equation by A. The left we can cancel. A over A is 1. T equals, we copy the right side, VF minus VO over A, and then we substitute. V final is 0 because the player stopped, minus the V initial is 3 meters per second. The V initial is positive because our player is moving to the right. So velocity is positive. To the right is positive. That is our sign convention here. To the right is positive. To the left is negative. A is negative 2 meters per second squared. Okay, so negative 3 meters per second divided by negative 2 meters per second squared. Executing using your calculator, you will arrive at an answer of 1.5 seconds. Again, we clarify why that is second. Let us do again the division of fraction. Meter per second divided by meter per second squared. Numerator meter per second, denominator meter per second squared. Numerator meter per second times the reciprocal of the denominator, which is second squared over meter. Meter over meter, that cancels, and second squared over second, you are left with 1 second in the numerator. So 1.5, that's the 1.5 seconds.